This is Dr. T. Siva Sankar Reddy, Professor of Civil Engineering, Lord's Institute of Engineering and Technology, Hyderabad. Today, we have the discussion on analysis of multi-story frame by approximate method, that is cantilever method. So to analyze the multi-story frame, we have three approximate methods. In that, first one is a substitute frame method, the second one is the portal method, and the cantilever method. We will apply the substitute frame method when the frame is subjected to vertical loads, whereas the remaining two approximate methods, that is portal method and cantilever method, are meant for analyze the frame when the frame is subjected to horizontal loads. So here in cantilever method, the important point what we have taken for the discussion is the methodology, what we can be approached to analyze the problem. Second one, for easy way to understand the problem, we have taken one problem for the discussion on cantilever method. For analysis of the frame, we should be concentrated on two assumptions mainly, because total analysis was based on these two assumptions. In that, first one is point of contraflexure or point of inflection or virtual hinge will occur exactly at the center of each member. So already you have read in your UC level what is the point of a contraflexure, or it's also known as a point of inflection, and third name for that is the virtual hinge. It is a point where the bending moment changes its sign or bending moment equals to 0. Come to the second assumption, what we can be follow to analyze the frame by cantilever method is the intensity of axial stress in each column of a story is proportional to horizontal distance of that column from the center of gravity of all the columns. How we can be evaluate the center of gravity of all the columns? After that, we can be take a discussion on that. That's why the analysis of the frame is carried out story by story. Now, today's discussion for the frame that we are seeing in the figure. The frame that we are seeing in the figure. First, we should be consider the top story of the frame. Let A1, A2, A3 and A4 be the areas of the columns AE, BF, CG and DH, which we have shown in the figure. H1, H2, H3 and H4 indicates the horizontal shears which are acting on the column seeing in the figure that we are seeing in the figure 6.11, whereas V1, V2, V3 and V4 indicates the vertical forces which are acting in the columns shown in the figure. So here first, as per the second assumption, what we know, what we can be right here is, what is the second assumption? Just now I told to you, the horizontal distance between the columns AE, BF, CG and DH will be proportional to the central distance of all the columns, which was represented by the dotted lines which we have shown in the figure. So as per the second assumption, which we should be followed to analyze the frame, what we can be right is V1 by A1 divided by X1 equals to V2 by A2 divided by X2 equals to V3 by A3 divided by X3, that equals to V4 by A4 divided by X4, where X1, X2, X3 and X4 are the distance of centroid of the columns AE, BF, CG and DH from the center of gravity of all the columns. Now come to how we can find out the values of the forces which are acting on the columns. So to find the values of the forces which are in the columns, we should apply the first assumption. What is the first assumption? The point of contraflexure will occur at the middle of all the members. So now you take the point of contraflexure at the middle of the column of a top story. If you observe the figure, what we can understand is, let P1 is the force which is acting at the joint A, that is on the top floor. If we apply the first assumption, point of contraflexure at the middle of the column, the equation that we can be present here is, let H be the height of all the columns, that is AE, BF, CG and DH. Now from the point of contraflexure, if we take to the middle of the columns, the equation what we can be present here is P1 into H by 2 equals to, or P1 into H by 2 plus, here we wrote equals to, but it is a plus V2 into L1 minus V3 into L1 plus L2 minus V4 into L1 plus L2 plus L3 equals to 0, where L1 is the, moment is the product of force and perpendicular distance. So the moment of force F2, V2 is V2 into L1, where L1 is the perpendicular distance with reference to the column AE. In the same way, L1 plus L2 is the perpendicular distance for V3, L1 plus L2 plus L3 is the perpendicular distance for V4. Now here, from these from these two equations, from the equation number 1, V1 by A divided by X1 equals to V2 by A divided by X2 equals to V3 by A divided by X3 equals to V4 by A divided by X4. And one more equation which we have framed here based on the assumption 1 is P1 into H by 2 plus V2 into L1 minus V3 into L1 plus L2 minus V4 into L1 plus L2 plus L3 equals to 0. If we solve these two equations, we can get the values forces in the members, that is V1, V2, V3 and V4. So if we know the values of these forces, considering the equilibrium equations, so already we have three equilibrium equations. One is the sigma V equals to 0, that is the algebraic sum of vertical forces equals to 0, or sum of the forces which are acting in the upward direction equals to sum of the forces which are acting in the downward direction. And the second equilibrium equation we have is sigma H equals to 0, that is algebraic sum of components of all the forces which are acting on the frame along the x-axis or along the horizontal axis equals to 0. And third equilibrium equation which is available to get the values of the horizontal shears which are acting on the columns are H1, H2, H3, H4 is sigma m equals to 0, that is the algebraic sum of moments of all the forces about a point equals to 0. So based on these three equations, sigma v equals to 0, sigma h equals to 0 and sigma m equals to 0, we can evaluate the values of horizontal shears in the columns AE, BF, CG and DH. So for easy understanding of the methodology, here we have taken one frame for the analysis by Cantilever method, which we have shown in the figure 6.12. So here we are assuming that the areas of cross sections of all the columns AI, BJ, CK and DL are same. Two loads are acting on the frame, one at 12 kilonewton, which is acting at the joint A shown in the figure 6.12, and a second load magnitude which mentioned is 24 kilonewton, which is acting at the joint E. The height of the top story is 3 meters and the bottom story is 4 meters, and distance between the two columns IJ 4 meters, JK 5 meters and KL is 6 meters. So here to analyze the problem, very important key value which need for us is getting the values of central distance of all the columns with reference to AI. Now take the moments of all the columns, moment of area of all the columns about the column AEI. So 4 into perpendicular distance is area of second column, 4 into A plus A into 9 plus A into 15 divided by total area of the column. 4 columns are there, each of equals to area A, that's why A plus A plus A plus A. Therefore, distance of centroid of first column with reference to centroid of all the columns is 7 meters. So x2 with a value of x1 equals to 7 meters, x2 we can get is 7 minus 4, that equals to 3 meters, which indicates the distance of centroid of second column with reference to centroid of all the columns. In the same way, x3 equals to 2 meters and x4 equals to 8 meters. According to second assumption, what we can be write here is VAE, where VAE indicates the vertical force in the column AE, VBF indicates the vertical force in the column BF, VCG indicates the vertical force in the column CG, and VDH indicates the vertical force in the column DH. From the second assumption, we can be write that VAE by A divided by x1 value we got is 7 meters. So VAE by A divided by 7, that equals to VBF by A divided by x2. x2 value here we calculated is 3 meters, that equals to VCG by A divided by 2, that equals to VDH by A divided by 8. So here A will be cancelled out. The terms which remains is VAE by 7 equals to VBF by 3 equals to VCG by 2 equals to VDH by 8. From this equation, what we can be write is VBF equals to 3 by 7 times of VAE, VCG equals to 2 by 7 times of VAE, and a force in the column DH, VDH equals to 8 by 7 times of VAE. You know that VAE and VBF, that is forces in the members AE and BF will act vertically downwards because it should satisfy the equilibrium condition. frame should fulfill the equilibrium condition. So based on the equilibrium equations, we can know that VAE and VBF will be acting in the downward direction. Remaining two forces, VCG and VDH, will be vertically upwards. Now take the moments at the midpoint of AE. If we take the moment at the midpoint of AE, here we consider the top story only. If we consider the top story, we should take only 12 kilonewton for calculating the values of forces which were in the columns AE, BF, CG and DH. So what is the equation that we can write here? Moment at the center of the column, because first assumption told that the point of contraflexure will occur at the midpoint of the column. So take the point of contraflexure about the column 12 into 1.50. Why? Because for the load of 12 kilonewton, here height of the column top story we have shown in the figure is 3 meters. So point of contraflexure will occur at the center exactly 1.5 meters from the point A. So 12 into 1.50 plus VBF, because it will be rotating the clockwise direction. We know that moment is the product of force and perpendicular distance. So here for the force VBF, the perpendicular distance is 4 meters. That's why plus VBF into 4 minus VCG into perpendicular distance there is 9. Why minus means it is in anti-clockwise or counter-clockwise direction. In the same way, minus VDH into perpendicular distance for force in the member DH is 15. So moment of that force about the center of the column should be equals to VDH into 15. That should be equals to 0. Why? Because it should fulfill the equilibrium equation sigma m equals to 0. You know, the algebraic sum of moments of all the forces about a point equals to 0. Now we framed the equation. If we solve the two equations which we wrote here, the values, the forces in the member we can get. The force in the member AE, VAE equals to 1 kilonewton. The force in the member BF 3 by 7 kilonewton, CG 2 by 7 kilonewton and DH equals to 8 by 7 kilonewton. Now we got the values of forces in the members. Next process is we should evaluate the values of horizontal shear on the column and also moment at each joint of the column, because here we can find the values only for the top story. We considered only the top story. Now here we make a discussion on that. Please concentrate on the figure 6.13. Now here the force in the column AE we got is 1 kilonewton. So definitely the force in the member's beam should be also 1 kilonewton. Here we have shown in the figure. Top story you please see. Come to the last column DH. Force in the member DH we got is 1.443. So automatically the beam also it should be 1.443. Now here come to the second column, that is second column. So 1 plus this one, the force in the member we got is 0.429, whereas the third column with reference to first column from left side, it is 0.286. Now come to the find the values of forces in the member. So 1 plus 0.429 equals to 1.429 is the force in the member beam. That middle beam we have shown the figure. Come to the second one, 1.443 and 1.443 plus 0.286 we can get is 1.429, or also we can verify from the left side 0.429 plus 1 equals to 1.429. Now come to find out the horizontal shear which is acting in the column. So here due to effect of 1, if we see the beam, first beam, If we see the beam, what happens is 1 kilonewton. The moment, the span which they have mentioned is 4 meters at the joint A. So 1 into 2, because span we have seen in the figure is 4 meters. We know the force will be act exact at the center of the beam. The moment of 1 about at the joint A we can get is 1 into perpendicular distance. So 1 into 2 equals to 2 kilonewton meters. It will be act in the direction of 1 only. To make the joint in a stable state or in equilibrium condition, we should be apply one more moment, 2 kilonewton meter in the opposite direction that we have shown in the figure at the joint A. Now here, what is the horizontal force, horizontal shear we can get in the column AE now? We know how we can get the moment. So we know moment equals to force into perpendicular distance. Therefore, the height of the first story we have seen in the figure is 3 meters. So moment at the point A equals to h into 1.50. Therefore, the horizontal shear we can get in the column AE equals to h into 1.50 equals to the moment 2. Therefore, horizontal shear on column AE we can get is 2 divided by 1.50. If we do the calculation, the value of h we can get is 1.333 kilonewtons. In the same way, you please see the next column. Now here, due to 1, what is the moment at the joint B now? All of you please concentrate at the joint B. What is the moment at the joint B? Due to force 1 now, due to force 1, the moment at the joint B we can get is span is 4 meters. So here force 1 will act exactly at the center. So the moment due to 1 at the joint B equals to 1 into 2, 2 kilonewton meter. That will be act in the direction of 1 only. That's why in the figure we have shown it is in counterclockwise direction. Now come to second beam, that is BC. If we see the BC, the force 1.429 will be at the center of a BC. So what is the moment at the joint B due to effect of force 1.429 now? 1.429 into perpendicular distance. Here span of BC in the figure we have mentioned is 5 meters. So the force will act exactly at the center 2.50 meters from the point B. So 1.429 into 2.50 is the moment at the joint B. Now here, what is the moment at the joint B? 2 will be in the direction of 1. And again 1.429 into 2.50 will be in the direction of 1.429 only. So definitely 3.572. If we observe the moments at the joint B, the value both are in the same direction. So the summation of the two values will give the actual moment which is acting at the joint B now. So 2 plus 3.572, the value will be 5.572 is the moment which is acting. So here to balance this moment, we should apply one more moment having the magnitude equals to 5.572 in opposite of that previous 5.572. Generally, the moment will be in equilibrium state or in stable condition. To get a moment of now, next our idea is we should find the value of horizontal shear on the column, second column BF. Okay, so how we can get the value of horizontal shear in BF? So force into perpendicular distance. So H into the height of the column, first story that we have shown in the figure is 3 meters. So H will be act exact at the center. H into 1.50 equals to 5.572. So the value of H we can get is 5.572 divided by 1.50. If we do the calculation, 5.572 divided by 1.50, the horizontal shear which is inducing in the column should be 3.7 3.715. Already we have shown with a arrow mark. Okay, 3.715 kilonewton. Come to the third column. If you take the joint C, what is the moment due to 1.429 now? 1.429 into 1.429 into 2.50, because the span of BC equals to 5 meters. It will be act at the center, so the perpendicular distance will be 2.50. Due to effect of 1.429, the moment which was developing at the joint C will be 1.429 into 2.50. It will be act in the same direction as that of this 1.429. The value we can get is 3.572 kilonewton meters. Come to the third panel, that is member CD. If we see the member CD, the moment at the joint C we can get is 1.143 into 3 meters. Why? Because span of CD we have shown in the figure is 6 meters. So 1.143 into 6 we can get is 3.429 kilonewton meters. If we observe the two moments which was developed at the joint C, all are in the same direction. So the summation of the two will give the total moment which is acting at the joint C. The total moment which is acting at the joint C will be 3.429 kilonewton meters plus 3.572 kilonewton meters. The total value we can get is 7.0 kilonewton meters. This 7.0 will be act in the direction opposite to the two moments, that is 3.572 and 3.429. Now we should find out the horizontal shear in the third column. What is the horizontal shear in the third column now? H into 1.50 equals to 3.572 plus 3.429, that is 7. So H equals to 7 by 1.50. The value we can get is 4.667 kilonewtons. So again come to the last column. Now if we take the last column, the moment what we can get due to effect of 1.143, here if we take the CD, the span we know is 6 meters. So 1.143 will be act exactly at the center. So the moment due to effect of this 1.143 at the joint D will be 1.143 into 3. The value we can get is 3.429 kilonewton meters. So to counteract or to compensate or to stabilize the joint or make the joint in equilibrium, we should apply one more moment of 3.429 in the opposite direction. Due to this 3.429 which was inducing at the joint D, so what is the horizontal shear we can get? Horizontal shear H is moment at the joint D, H into 1.50 equals to 3.429. Therefore, horizontal shear that we can get is 3.429 divided by 1.50. Even though if you calculate, the value we can get is 2.826, 2.286 kilonewtons. This is the process what we can adopt to analyze the cantilever frame or maybe frame by cantilever method to evaluate the values of vertical forces, horizontal shear and also moment which was inducing in the frame. So we should adopt the same procedure to calculate these values for the bottom story also. So knowing the vertical forces in the columns, already you are well known how we can find out the values of vertical forces. We can evaluate the values of what we done just now, beam shears, beam moments, okay, by considering the equilibrium of the joints. Thank you one and all for viewing my video.